welcome to 6150, and this is Advanced Algorithms. My name is Aditya Bhaskara, and so hopefully all this setup will work, because this is the first time I'm also trying this, and I guess it's the first time the video is also being recorded. Is it? Okay. Alright, so good. So now, okay. So firstly, how many of you are first year students, either masters or PhD? Okay, actually then how many of you are not first year? Okay, so there's a fair number of folks. Okay, alright. And actually, are most people here masters? How many PhDs are here? Okay, I see. So that's a good mix, I guess. So we have people from varying background, which means that if you don't follow anything, just feel free to raise your hand and ask a question. And yeah, some of these things might be a bit too slow if you've seen most of the material before, but that should be fine. So hopefully the homeworks will make up for it. Okay. So, all right. So is there a reasonable undergrad population? How many of you are undergrads? Okay, so this is a relatively smaller number. Okay. And the other thing I wanted to ask you guys first about is your background. Okay, so how many of you have done an algorithms class in the last 3 to 4 years? Okay, so that's great. Yeah. So I don't have to spend too much time in the introductory part. So that's good. And what about discrete math? So this class will be more about proofs, and actually instead of implementing algorithms, we're going to try to reason about them. Okay. So how many of you have taken a discrete math class? Oh, you did. That's fine. Yeah. Okay. So excellent. Okay. So let's start with the basic outline of the course. Okay, so what are the motivations for this course? So firstly, what is an algorithm? So an algorithm is algorithms are something that show up in all aspects of computer science. They're one of the most basic things. And an algorithm is simply a sequence of steps. Okay, so you have some input and you want to do something interesting with it. And how exactly you do this is what is described by an algorithm. So that's the basic definition, and I guess all of you have seen at least algorithms in some form or the other. Okay. And as I was saying, it's a basic aspect in all of CS. Okay. And recently it's gotten press attention also. I think everybody is catching on to the fact that there's something interesting. Okay. So you can see how you can save the world and so on with using algorithms. Okay. But more realistically, what we will care about in this class are things like the following. Okay, so we'll think about how to design efficient algorithms. Okay, I'll describe what that means in a second. So we're going to try to measure various forms of efficiency. Okay, and the course will focus on general principles of algorithm design. Okay. So there are these broad ideas like divide and conquer and dynamic programming and so on. And part of the goal of the course will be to kind of illustrate these basic ideas. And we'll look at certain representative problems. We'll try to see how you can design efficient algorithms for these. Okay? So that's the main goal of the course. And we also want to figure out how to analyze algorithms. Okay? So given an algorithm, you want to reason about things like, what is the running time of this? Okay, so suppose I give you an input of size n. What is the asymptotic running time of such an algorithm? Okay. So these are the kind of things we will care about. Okay, and sometimes we'll care about things like memory usage and so forth also. Okay. And the last thing is proving the correctness of algorithms. Okay. So this is something maybe not all of you would have paid too much attention to. But we will always care about showing that an algorithm does what it's supposed to do. Okay? And you often prove it mathematically using induction or something like this. Okay? And reasoning about algorithms is very important. I mean, given that you've already seen that it's used in so many fancy applications, it's important to have correctness. Okay? So you want to prove mathematically that algorithms are correct. Okay. And at this point, I guess it's natural to ask, are we going to do any programming in this course? The answer is not explicitly. Okay, so if you want, you can do a programming project as a course project. Okay. But all the exercises, homeworks and so on will not touch about programming. Okay. And this is not to say that programming is not, it should be in the back of your mind. Okay. So this is not something we'll explicitly study in class, but any algorithm that you write down, you should at least in principle be able to implement. Okay. So, and this is quite important. Okay. So here I guess. Yeah, so it's just not explicitly. Okay. And when you are describing an algorithm, it's always important to keep in mind how you would implement it. Okay, because it's very easy to say, oh, okay, do this, but you have to actually describe how exactly you do this. Okay. So even though we're not actually implementing, you have to keep an implementation in mind. Alright, so that's the basic outline of what the goals are of this course. Okay. And any questions about this? Alright, logistics. So firstly we will use Canvas for submitting all homeworks and for other course information. So I think there are different Canvas pages for 6150 and 5150. So I guess there are very few people enrolled in 5150, right? Just the undergrads. Okay. So I'll try to see if you can get access to 6150 page, because that way we don't have to update 2 pages. So all the videos of the lectures will be there, and some of them might even be publicly uploaded, but we are not sure. And let me introduce the teaching assistants. I'm lucky to have 3 very good teaching assistants. So I guess if you can all stand when your name is called out. So the first year will be Mohsen, and he will have his office hours on Tuesday from 3:30 to 5:30 p.m. And the other one is Michael, and his office hours are these. And another final year is Weiming, who has office hours on Friday. So assignments will mostly be due on Friday, and except for the 0th assignment, which I'll post today, and it won't count towards your grade, but it will give you a taste of how assignments will be like. Okay. So, and as you'll also see, I want to encourage the use of LaTeX. So the 0th assignment will give you practice for that also. Okay. So any questions about logistics so far? Okay, and I guess another important thing is grading. Okay, so there will be 6 homeworks. There will also be homework 0, but as I said, it's ungraded. And these 6 homeworks will be most of the grade. And there's a project and a final. Okay. So the project can either be an implementation project where you take some algorithm and apply it to some interesting data set, or it could be reading a paper. Okay, so the details of this project I'll put up in a week or so, or maybe in a couple of weeks. Okay. But that's the goal of the project. There will also be a final in the usual final suite, and it will basically look similar to the homeworks, but it will be shorter, and it will be time constrained. Okay. Alright, so these are, any questions about the grading? Yeah.
Will the final be on a computer and LaTeX as well, or?
No. So the final will be a written one, because in a time constraint setting, Yeah, at least I feel for first time users it's not fair. Okay, so this is what I was saying earlier. So LaTeX, right? So there's this perpetual debate. I mean, should all computer scientists be forced to do LaTeX or not? And you know, I at least feel that all computer scientists worth their salt should use LaTeX. Okay. So okay, so I wholeheartedly agree with the first guys. Well, using PowerPoint myself, I should probably not be saying too strong. And anyway, so I'll have templates out. So how many of you have never used LaTeX before? Okay, there's a significant chunk. So you've got to. I'll post a link to some basic introduction. Okay, and it's actually very easy. It's nothing daunting. It'll just, you have to get used to it for a little bit. Okay, so I would encourage all of you who haven't used it to submit homework 0. Okay, and then if you have problems, you can ask the TAs. And on this note, there's also a LaTeX boot camp, which a fellow faculty will be running in the department. It's a while from now, but until then, you can use some of the resources. Okay, so some of the TAs or some of the links that we put up. Okay, and needless to say, all homework deadlines will be strict. So maybe one or two of you have emailed me saying you have certain emergencies. So maybe for those I'll allow like a couple of days more. But otherwise, deadlines will be strict. Yeah, just because in a class of this size, it's hard to manage otherwise. So, all right. And what about collaboration? Okay. So, most of the problems, as I said, will be kind of theoretical in nature. So, you'll have to write a proof and come up with an algorithm possibly. Okay. So, you are allowed to discuss with people. So, just discuss the ideas and that is fine. And list everybody whom you discuss with. Okay. So that is the only official requirement. And if you look up certain things online, then also please give references. Okay. And there's also an official policy, hopefully we'll never have to use it. Okay, so any questions about grading, homework, etc.? I'll come to sample homework questions and give some examples of how the course will be like. Okay, so let's look at prerequisites. As I said before, taking an undergrad either algorithms or discrete data structures course will be extremely helpful and to some extent necessary. Okay, so if any of you have not done either one of these courses, like if you've not done either course, then I would recommend that you do one of these things first and do advanced algorithms in the spring. Okay. So this is another announcement that I forgot to put up on the slides. This class will also be offered in the spring. Okay. So if you guys think that you have too much on your plate this semester, you can also do it in the spring. Okay. But on the other hand, this is a basic course, so it's good to get it done. So that's the argument. Sorry? Oh. Okay, so basic data structures. So I'll assume knowledge of things like arrays, lists, and binary search trees and so on. So have all of you seen binary search trees? I guess everyone would have used an array. Everyone who coded would have used an array. And what about the big O notation? Everyone seen? So suppose I define T of n to be that. So what would you say? It's big O of what? Okay, good. Yeah, so alright. And another basic question. So suppose you have to sort n numbers. Okay, so you have an array of size n. How long does it take to sort an array of n numbers?
N log n. N log n.
More mixed reaction, I guess n log n is the majority answer, so that's good. Okay, so that's the best way you can sort n numbers. So, alright, so these are the basic kinds of things that you learn in a intro to algorithms course, so I assume some knowledge of it. Okay, and the other thing is I'll assume some knowledge of discrete math. Okay, so when somebody says a graph, what do you think of? The left side or the right side? The right side, right? Okay. So this is crucial. Okay. So, alright, so I'll assume some knowledge of what it means to say a vertex, like these numbered things are vertices and the lines are the edges and so on. Okay, and just to like go with this background thing a little bit more, so let's start with a simple puzzle. Okay, so suppose I give you an array of n numbers, and it's sorted. Okay, so an array has indices that go from 1 through n, let's say, and you know that a of 1 is less than a of 2, less than so on. Okay. And now I give you a number x, and I ask you to find out if this number is in the array or not. Okay, great. So all of you, how many of you have not seen this? I mean, it's fun. I mean, okay, so I guess all of you have seen it, or all of you seen it in some form or the other. Okay, so let's go through this example just to see what it means to prove that something runs in a certain time. Okay, so this is like a very extremely simple example, right? Okay, so we have a bunch of n numbers, and I give you some number x. You want to find out if it's in the array or not. Okay. And the key thing here is that it's sorted. So all of you have already said that it takes roughly like log n steps, but the most naive way you can think of is start at the beginning and you just search, right? And what time does that take? That takes n time, and you want to do faster. Okay, so that's clearly the goal. And let's see if this works. Okay, so you have this array of n numbers, okay, which I call A, and this is A1, A2, up to AN. Alright, so we have something like this, and we are given some number x. Okay. So let's write some numbers here just to, maybe it's like -1, 0, 2, 4, something like this. Okay. And the goal is to find x in this array. So how does this work? Okay, so how would you do this in time that is only log n? Okay, so that's the word for it. But what you would do is, so you want to kind of keep reducing the search space. Okay, so that's the idea. So initially you know that your x, if it exists at all, is somewhere in this whole interval, right? So it's somewhere in this whole range. But one way to reduce the search space is to say, okay, I look at this middle element out here, and I'm going to see if x, I'm going to first check if x is that element, I mean if that element is x. If it is, then fine, and you found it. And if it's less than x, okay, so suppose this element is some x minus 10, okay. So then you know that, so then where should x lie? X should lie potentially to the right, right? So if it lies anywhere, it should lie on the right. So this is where x should lie. And now what you've achieved in this process is that you've reduced Yeah, so you reduce the candidate search space to half, right? And now you can keep doing this in the sense that next time you could look at this guy and then see if it's on the left of this or right of this, and keep going. Okay. So good. And so this is what keeps happening. So if you do k such iterations, so the first iteration you'll have a candidate set of size n, you'll have a candidate set of size n over 2, and so on. Okay. So if you do this k times, you'll have a candidate set of size n over 2 to the k. Okay. And you try to see when that becomes small enough that you can just do a brute force search. Okay. So if you reduce this candidate set to size 1, okay, then it means that x should either be that element. If it's that element, then it's fine, you found it. If not, then you know that x doesn't exist in the set. Okay. So what I've said here is also the proof, right? So you should just pay attention to this fact that I've actually formally proved that if x does not exist in the array, then this procedure will certify. Okay. So this last step of the recursion is something that you should, it's also important. Okay. So this is like the base case. Okay. And yeah, so the base case is when n over 2 to the k is roughly a constant. Okay. So it's maybe 1 or 2. And in this case you can just search. I mean, you can just check if x is that element or not. Okay, and if you work this out, so this just means that k is roughly log n to the base 2, and this is where you get this running time. Okay. And yeah. There's also, each time you do a constant number of operations, it's not exactly one operation. So you have that the total running time is O of log n. Is some constant times log n to the base 2. And this we write it as O of log n. Okay. Alright, so this is just to illustrate to you how you should like formally reason about things. Okay, so that's about the background. Okay, so I'll assume basic knowledge of the kind of things that I've shown so far. And now let's look at the course outline. Oh, okay, so let me actually move to... Okay, so this is something I couldn't figure out how to put this on canvas, so and I'm assuming the TAs will help me out with this. So this is the outline for the course. Okay, so these are the topics that we'll cover. So there's a link to this now on Canvas, but it'll actually be on Canvas soon. Okay, and this is where video links and so on will be posted. Okay, and so what are the main parts here? So first. For the first few weeks, okay, this is all on a weekly basis. The first few weeks we'll basically do the essentials. Okay, so these are things which most of you would have seen in one form or the other, but we'll try to do things rigorously, and we'll try to kind of set the stage for the rest of the stuff. Okay, so this review of basic algorithmic paradigms is essentially things that you should have seen in some form or the other. Maybe except with the possible exception of approximation and things like gradient descent and so on. How many of you have seen gradient descent? Oh, excellent. Okay, so then yeah, so then most of you have seen most of these things. And we'll also do a little bit of approximation algorithms, where so this is following NP hardness. Okay, so some problems are difficult, but you still want to do well. Okay, so that's approximation algorithm. And then we'll move on to algorithms on graphs. Okay, so there again, many of you would have seen shortest paths and spanning trees. Okay, so that we will just recap. And then we'll do some very interesting things for flows, matchings, and so on. These you might have seen, but you will discover that there's so much in this space that there's always room for new things. Okay, so we'll do that, and so that is until the spring break, or we won't have a midterm, so that's roughly until the spring break. Okay, and then we'll do something about randomization. Okay, so this is where you'll have some very new stuff coming up. So how many of you have seen probabilistic algorithms where you toss coins to make decisions? Okay, so there's the reason why you don't know.
I don't know.
You build your
Forever?
no. Are you a grad student at Suresh?
No.
Oh, okay, then I'm mistaken. Yeah. So, I thought you were Suresh. Okay, so all right. So we'll see something about randomization. Okay, so these are basically algorithms where you rely on chance to succeed. Okay, so you make arguments like if I toss a coin 10 times, with very good probability I'm going to see one heads. Okay, and things like this. Okay, so you try to show that you try to design algorithms where failure probability is extremely low. Okay, and in practice, when you actually are running something, that's what suffices. Okay, so that's the idea behind randomization, and you'll see that it's actually used everywhere. Okay, so like hashing is one important application where you rely on good properties of hash functions and so on. Okay, so these are things that are extremely useful, particularly if you plan to do data mining and things like this in the future. So that's the third part of the class, and then we'll actually start talking about optimization. So optimization is this very powerful algorithmic framework where you can try to phrase various problems as optimization problems. Okay? And this is something you would often do in practice. Okay? So I mean, let's say you are working in the industry somewhere and a new problem comes up. Okay? So you can either start to develop an algorithm from scratch, or you can try to phrase it as some well-known optimization problem and try to use known methods to solve it. Okay? So this is something that is very important to know, particularly when you're dealing with new problems. And we'll see that towards the end. And we'll also talk a little bit about distributed algorithms. And this again, with data becoming large and so on, most algorithms these days are distributed. So there are these interesting trade-offs, like there are some things that you can do naturally in a distributed way and some things that you can't. Okay? So that's what we want to understand. And we'll see some basic models like MapReduce and so on. Okay? And depending on time, we might do some multiple fun topics where kind of get to see different aspects of algorithm design. Okay. So, any questions about the class schedule? I guess if you have concerns about specific topics, do email me. This is not set in stone. I mean, this could be changed. There's good motivation for this, but parts of this could be changed. Okay, so that's.
What is a project view?
Okay, give me 1 second. I'll try to figure out how to maximize this. Okay. Alright, so you said what about the project?
What is a project view?
The project is, I was thinking at the end of the semester, so maybe the last week of class would be a good time. Okay, so the week of November 29th. Okay, so is that fine? So, or do you guys prefer, we could also do it like right before the exam. Okay, so that's fine too. But I think it is good if you do it, if you submit it maybe during this week when we are doing a course review. Okay, so something like December 1st or something like that. Okay, so I will, yeah.
Projects individual?
So that again, I will get back to this because this will depend on how many students are in the class. Like right now there's certain population, maybe in a few weeks it will be lower. So depending on that, so I would prefer an individual project given that it's a small percentage of the grade. But if it's a large enough class, I think it makes sense to have 2 people, groups of 2 at least. So I will finalize this in a week or so. Okay, after talking to the TAs also, I guess they'll have input work. Okay, so alright. So as I was saying, so these will be the first 2 topics, and then we'll have the fall break, and then we'll do these other topics. Alright. So let me. Yes, I was planning to end quickly today, but we can do a little bit of. So I wanted to just give you an illustration of what types of problems we'll be considering in the class. Okay. So in general, I want to give some sense of the different kinds of problems that arise. Okay. And the first kind we'll see are numeric ones, where I call them numeric, but in some sense they're very combinatorial. It's like you want to sort a bunch of numbers, or you want to find the median of a bunch of numbers, and so on. So that'll be the first kind of numbers that we'll see, of problems that we'll see. And we'll also look at a few optimization type problems where you want to minimize some function. Okay, so you have a function of multiple variables, and maybe you want to minimize it or something like this. So that's the other kind that will show up. Okay. And third kind are graph problems. Okay. So again, one example could be, we want to find a bunch of vertices in the graph that all have edges between them. So does anyone know what this problem is called? So you want, you want to find a bunch of vertices that have all possible pairs of edges. A con is like connected. So this is called the clique problem. Okay, so you want to find a bunch of people who are all connected to each other. Okay, so that's called the clique problem. And and then we'll see other things. Okay, so when we talk about online algorithms, we'll come up with problems that seemingly have some practical motivation, like should you rent skis or should you buy them, and so on. Actually, the more realistic setting for this, which is used a lot, is in when you're designing some memory hierarchies. How do you handle cache misses and so on? Okay, so for those of you who know, this is what most of online algorithms is about. Okay, so these are the kinds of problems that you'll be seeing. This is not an exhaustive list, but this is just a sample. So you'll see a bunch of diverse set of problems. Okay, so that's the message I want to give. Okay, so apparently my slideshow there is not updated, so I will. So I wanted to also generally give you some sense of the kind of problems that we'll be using for homework. Okay, so this is just, so there are some slides that somehow did not get updated on this. So I just wanted to show you some of the other things that I wanted to say. Okay. So as I said before, all the homeworks will be, you want to come up with algorithms and you want to prove that they are right. Okay. And they'll mostly be reasoning. So you don't have to really code up the algorithms that you design. Okay. And as I was saying, so this is an example. Okay. So given that we did, yeah.
How formal is the person?
Yes. So we will get to that. So I think this will be like a iterative process. So that's why I encourage all of you to submit homework 0, so that you get feedback on how formal it should be. Okay, so homework 0 and 1, I expect that they will work towards establishing this. Okay, so I think so. Try to be as formal as you can. Okay, try to essentially prove. I mean, for instance, if you have to prove something by induction, then you have to prove something by induction. Okay, so that's the level. But sometimes people could be too formal, in which case we will tell you. Okay, so the level at which I did this binary search example is what I would expect. Okay, so you try to give the rough idea behind the algorithm, then mention what formally the procedure is, and then show that it actually works. Okay? And you've got to analyze its running time as well. Okay? So as I said, it looks pretty tedious, right? So there's a lot of steps that you have to do, but soon it'll just you'll get used to it. Okay? So don't worry too much. Okay? And given the importance of these things, it's useful to be able to do this whole process. Okay, so this is an example, and just to illustrate this question, I wanted to go through this homework example so that you guys know at what level I would expect. Okay, so unfortunately, this thing doesn't write, so we'll quickly try to solve this homework example just to illustrate. Okay, so this is given that we've seen the analysis for binary search. Okay, so this will hopefully be easy. Okay, so that's the hint. So any ideas? So the problem is the following. Okay. Yeah. Give me 1 second. Let me explain the problem. Okay. So the problem is you're given a sorted array of n integers. Okay, so I guess the question is not very formal. It should be n integers, and you want to find out there's some index I such that a of I is equal to I. Okay, and again, it's important that it's sorted. So I get a blank screen. Okay, so we have an array, and this again, as before, it has size n. Okay. And the goal is find I such that ai equals I. And again, as before, you know that A1 is equal to A2. Actually, you need strictly less than for this problem. Okay. So you know that A1 is strictly less than A2 less than AN. Okay. So, alright. So now let's see why this should be at the end. Okay. So part of this algorithm design is try to figure out when an algorithm works and when it doesn't, right? So we try to see why it's important that you need strict inequality. So, okay, so how do you find such an n? How do you find such an I? So you're saying...
Just modify the binary search condition.
Okay.
Instead of comparing it with x, you just compare it to their position. And you eliminate in this system.
Okay, so what he's suggesting is try to mimic binary search and do the natural modification. Okay, so let's say I look at a n over 2, and let's say this is this position. Okay, and so the algorithm formally, so I'll try to illustrate how you should write it. Okay, so the algorithm formally is at every step you have this interval that you're considering. Okay, so you have an interval which I'll denote by a start and end. Okay, and so initially you'll set start to equals 1 and end equals n. Can everybody read this by me? Is it big enough? Okay. So you'll initialize with this, that every time step you'll have this interval. Okay. And now you will look at this index. Okay. So you'll look at the index which I will denote by start plus n by 2. Okay. So this is the middle of this interval. Right? So if you have an interval that starts off at some number and ends at some other number, then the average of these two is s plus e by 2, right? So is that clear? Okay. And for now I won't write floor, ceiling, something like this, so you have to do that formally. Okay, so let's by default it's ceiling. And so now you look at this index, which is, informally speaking, that's the middle index. Okay. And you want to first see if this index is the right one. Okay, so you want to see if, check if, yeah, exactly. So if a of idx equals idx. Okay, so now there are three things, right? So if a of idx is equal to idx, then it's great, you found one such I. So if so, you find, if yes, great. Okay, and otherwise there are two options, right? So a of idx could be smaller than idx, okay, or it could be bigger. Okay, so what do you do if it's smaller? So what do you do if it's smaller? Yeah, so okay, so that's what I was wondering if I should do it that formally or not. But what it intuitively means is that whatever you're looking for cannot be on the left. Okay, that's just because a of idx itself is a of idx is smaller than idx. So all the integers that precede it, they are in strictly decreasing order. So you can't have an index such that a of I equals I. Okay. And this is where I claim it's important that you have strict inequality. So can you guys see why the strict? Yeah.
Repeating numbers, right? So if they are repeating numbers.
Yeah, exactly. So if you know that, right, so you could have an interval where you have 1, 1, 1, 2, 3, 4, let's say. And now you check this middle guy, you found that a of idx is smaller than the index itself. Okay, so the index is 3 and the number is 2. Okay, but this is not good because, I mean, the index that you really want is actually over here. So, yeah.
Don't you also require that a sub I are integers, right?
Yes.
On them?
I do require, yeah. So AIs are integers and they are strictly increasing. Okay. So this is what you need to argue. Okay. So you have to say that because they are integers, because they are strictly increasing, if you find that a of idx is less than idx, then none of the indices before s could satisfy this constraint, this condition. And then you do the natural thing, then you say that, okay, now you set start to be idx and end to be whatever, end to be end itself. And otherwise you do the complementary thing. Okay. So this is the level at which I expect proof to be. Okay, so this is why I'm working through this example. Okay. So you've got to clearly state the reason why you can actually do this. Okay? And in the end, you've got to prove that if there exists an I such that ai equals I, then you'll actually find it. Otherwise, you'll report the correct answer. Okay. So that's what I wanted to illustrate. Okay. So is the example clear? Yeah.
I could be missing it, but I don't see any type of looping happening in this example.
Yes. Yeah. I should do this. So what I should say is, if it's bigger, then I go to this, and then I actually just go back to this. Okay. And there should be a break clause that says that if start equals end, then you just check if that index works and then quit. So, right. So I guess when you're writing the algorithm, you have to have some form of pseudocode. Okay, and the pseudocode should look roughly like this. Okay, and it should also have the loop and so on. Okay, and as you will see, initially it's good to be very careful with these things because it's easy to miss certain things, and especially when you're actually coding these algorithms, right? It turns out conceptually simple things could create a lot more headache than you would want. Okay, so it's good to be as formal as possible. Okay. So, yeah.
So, I'm still a little confused with what you said about A IDX is less than IDX.
Mm-hmm.
I don't see how that applies to the example you gave at the top.
Yes, so in this example, I'm assuming indices start at 1, right? So this is A1, this is A2, A3, A4. Yes, right? So in this case, A4 is actually 2. Okay, so 4 is IDX in this case. Okay, and what I'm saying is that A4 is actually less than 4 because 2 is less than 4. Okay. And so that's why we are in this case.
But the answer is on the left.
That was a counter.
So this was actually a counter example. So I was just saying that in this example, I don't have strict inequality. Okay. So and I was just trying to argue that somehow the strict inequality is important in the problem statement. Okay. So it's important that you have distinct numbers. If you allowed equality, then you could come up with a counter examples like this. Okay. So right. So if you actually had strict inequality, then this is not an allowed input, right? So this has to be something strictly smaller, where maybe here it's 1 and then there's 0 and -1 or something. In which case there is no answer. Okay. So yeah, that's what I wanted to illustrate. I just wanted to say that it's important that you don't have equality. Okay. And this is the sort of a thing that you realize only when you formally try to prove it. Okay. So that's why I was saying it's good to be as formal as possible when you start out, and then slowly you can give yourself more, you'll get used to the argument, so you can give yourself more slack. So that's a good question. So any other questions? Yeah.
Will you publish solutions to the homeworks after you're ready?
Yes. Yeah, of course. Yeah. So we will. I don't know what the best way is. Is it better to just do it on Canvas? Probably. Okay. So we'll just do it on Canvas. And yeah. So this is another reason why it's very important that you hand in homeworks on time. Okay, so that we can post solution. Yeah.
Let me go back to the actual question. I just don't know if it said that they had to be distinct.
No, the question was actually, it was from a previous homework, and it was stated very informally. Okay, so it did not even say that they were integers.
I was just wondering if we run into that in our own homework. Or we don't.
No. So I'm very picky about these things, so you will not. Okay, so and also I know that the TAs are very meticulous. I taught them a class last semester, so they will not do it. Yeah.
On the homeworks, are you looking for one specific answer, or are there multiple correct?
No. Multiple correct answers are fine. As long as the argument is fine, you will get a credit. Okay. So any other questions about homeworks? Yeah, I would suggest just do homework 0, and then it will give you a general idea of how it will be done. Okay. So the others could be more difficult, but it will be of the same kind. Okay. so this is one thing I wanted to say. And yeah, again, as I was saying, initially it will look tedious, soon you will get used to it. Okay. Alright, so that's essentially what I wanted to say. What I was saying, I wanted to end quickly today. So next class we'll actually start with the actual course. So we'll do this, we'll cover this basic idea called divide and conquer. Okay, where you have a problem and you try to break it up into sub-problems. Okay, and try to use the solution to these smaller pieces and kind of patch together a solution to the full problem. Okay, so this is a very general algorithmic paradigm, and we'll see some examples of it. Okay. And in the process, we'll see how to analyze running time of algorithms when you do things like this. Okay. So, alright, see you.